This is SpaceTime Series 24, Episode 79. Coming up on SpaceTime, discovery of a white dwarf so massive it might collapse, a new hypothesis to explain Mercury's huge iron core, and planet Earth's hot new neighbour. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered the most massive white dwarf ever seen. The smouldering cinder, which formed when two smaller white dwarfs merged together, is now packing a mass greater than that of our Sun, squeezed into an object no larger than the Moon. White dwarfs are the collapsed cores of Sun-like stars. Stars shine by fusing hydrogen into helium in their cores. When they run out of core hydrogen, they contract, eventually increasing core temperature and pressure to the point where they begin fusing core helium into carbon and oxygen. At the same time, a shell of hydrogen begins burning outside the core. And this causes the star's outer gaseous envelope to expand. And as it's now further away from the contracted core, this outer envelope also cools down, turning the star into a red giant. Now, eventually the star will run out of core helium to fuse, and as it's not massive enough to fuse carbon and oxygen into heavier elements, the star dies. Its bloated outer envelope floats away as a spectacular cloud of gas and dust called a planetary nebula, while its white-hot stellar core lies exposed as a white dwarf, a superdense object usually about the size of the Earth, which will slowly cool over the eons. Astronomers think about 97% of all stars in the universe will eventually end their lives as white dwarfs. This unusual new discovery, catalogued as ZTF J1901 plus 1458, was made by the Zwicky Transient Facility at Caltech's Palomar Observatory. So, how did this white dwarf get so massive? Well, unlike our Sun, most stars exist in multiple star systems, and this new discovery provides an example of what could happen in a multiple star system after the formation of a white dwarf. A pair of white dwarfs were in a binary system, spiralling around each other and eventually losing energy in the form of gravitational waves, which ultimately led to them getting closer and closer together until they eventually merged. Now, usually when two white dwarfs merge, there's enough mass there to trigger a thermonuclear or Type 1a supernova explosion. But if they're just below that threshold, which is around 1.44 times the mass of our Sun, then instead they'll simply combine to form a new white dwarf that's heavier than either of the progenitor stars. But this process of merging boosts the magnetic field of the new star and speeds up its rotational rate compared to that of its progenitors. Astronomers believe that this newly found white dwarf took this latter route of evolution. Its progenitors merged and produced a new white dwarf with about 1.35 times the mass of our Sun. A report in the journal Nature says this newly discovered white dwarf does have an extreme magnetic field, almost 1 billion times stronger than that of our Sun. And it's spinning round on its axis at a frenzied pace of almost one revolution every 7 minutes. Now, by comparison, our Sun takes about 30 Earth days to complete each revolution. The study's lead author, Ilaria Caiazzo from the California Institute of Technology, says while the white dwarf wasn't quite massive enough to explode in a supernova, it might be massive enough to evolve into a neutron star, which typically forms when stars far more massive than the Sun explode in core collapse supernovae. She admits it's highly speculative, but it is possible. Caiazzo says it's so massive and dense in its core that electrons are being captured by protons in the nuclei to form neutrons. Because the pressure from the electrons pushes against the force of gravity keeping the star intact, the core collapses when a large enough number of electrons are removed. Now, if this neutron star formation hypothesis is correct, it could mean that a significant number of other neutron stars out there could also be created through the same process. The new found object's close proximity to the Earth, just 130 light-years away, and its young age, just around 100 million years or so, indicate that similar objects may occur commonly in our galaxy. The thing is, no one's been systematically able to explore short timescale astronomical phenomena of this kind on this sort of scale until now. The authors analysed the spectrum of the star using the Keck Observatory in Hawaii. They found signatures of a very powerful magnetic field, and that suggested that they had found something very special. The strength of the magnetic field, combined with the fast 7-minute rotational speed of the object, indicated that it was probably the result of two smaller white dwarfs coalescing into a single object. Data from NASA's Swift Space Telescope, which observes in ultraviolet light, then helped nail down the size and mass of the white dwarf. With a diameter of just 4,300 kilometres, ZTFJ 1901 plus 1458 now secures the title for the smallest known white dwarf in existence, edging out the previous record holders, who were each around 5,000 kilometres across. And as you'd expect, the authors are now searching for more white dwarfs like this one, so they can study the population as a whole. The thing is, there are so many questions to address, such as what's the rate of white dwarf mergers in the galaxy, and is it enough to explain the number of Type 1a supernovae that are seen? Also, how's a magnetic field generated in these powerful events? And why is there such diversity in magnetic field strengths among white dwarfs? Finding a large population of white dwarfs born from mergers will help provide some of these answers. This is SpaceTime. Still to come, a new hypothesis to explain Mercury's huge iron core, and planet Earth's hot new neighbour. All that and more still to come on SpaceTime. A new study claims that rather than being the result of a massive collision blasting away much of its mantle, planet Mercury's proportionally massive core could simply be the result of exactly where in the solar system the planet was formed. For years, astronomers have speculated why the nearest planet to the Sun has such a huge iron core compared to its relatively small mantle. See, Mercury has a metallic core that makes up about 3/4 of its overall mass. By comparison, the cores of the Earth and Venus only make up about 1/3 of their mass. And as for the planet Mars, it has an even smaller core, making up only about 1/4 of its mass. In the case of Mercury, hit-and-run collisions with other bodies, blowing away parts of Mercury's rocky mantle during its formation, was long considered the most likely reason the planet has been left with such a huge, dense metallic core. But a new study, reported in the journal Progress in Earth and Planetary Science, suggests that the Sun's magnetism, rather than collisions, is more likely to blame. The findings are based on models showing that the density, mass and iron content of a terrestrial or rocky planet's core is influenced by its distance from the Sun's magnetic field. The study's lead author, Professor William McDonough from the University of Maryland, says the solar system's 4 inner planets, Mercury, Venus, Earth and Mars, are each made up of slightly different proportions of rock and metal. And he says there's a gradient in which the metal content of the core drops off as the planet gets further away from the Sun. And the new model explains how this could happen by showing that the distribution of raw materials in the early forming solar system 4.6 billion years ago was controlled by the Sun's magnetic field. McDonough's new model shows that during the early formation of the solar system, when the young nascent Sun was still surrounded by swirling clouds of gas and dust, grains of iron were drawn towards the centre by the Sun's magnetic field. So when planets began to form clumps out of this gas and dust, planets closer to the Sun incorporated more of the iron in their cores than those which are further away. McDonough and colleagues found that the density and proportion of the iron in a rocky planet's core correlates with the strength of the magnetic field around the Sun during planetary formation. The new study suggests that magnetism needs to be factored into future attempts to describe the composition of rocky planets, including those outside our solar system. The composition of a planet's core is important for its potential to support life. On Earth, for instance, the molten iron core creates a geodynamo, which in turn creates a magnetosphere that protects the planet from cancer-causing solar wind and cosmic rays. Using existing models of planetary formation, McDonough determined the speed at which gas and dust was being pulled into the centre of the solar system during its formation. He then factored in the magnetic field that would have been generated by the Sun as it burst into being, and calculated how that magnetic field would draw iron through the molecular gas and dust cloud. As the solar system began to cool, dust and gas that were not drawn into the early Sun began to clump together, and the clumps closer to the Sun would have been exposed to a stronger magnetic field, and thus they would contain more iron than those further away from the Sun. And then, as the clumps coalesced and cooled into spinning planets, gravitational forces caused differentiation, driving the iron into their core. When McDonough incorporated this model into calculations for planetary formation, it revealed a gradient in metal content and density that just happened to correspond with the core-to-mass ratios for the planets. This is SpaceTime. Still to come, Planet Earth's Hot New Neighbour, and the final mission of the Cygnus 15 cargo ship. All that and more still to come on SpaceTime. Astronomers have discovered a new exoplanet in our part of the galactic neighbourhood. The newly found planet, Gliese 486b, is a so-called super-Earth, larger than the Earth but smaller than the ice giants like Neptune and Uranus. It's orbiting around a spectral type M red dwarf star, and it's not far away, just 26 light-years, so that does really make it one of our closest neighbours, galactically speaking. Red dwarfs are the most common types of stars. In fact, they're thought to make up around 70% of all the stars in the Milky Way galaxy. The exoplanet is orbiting extremely close to its host star, taking just 36 hours to complete each orbit. Now, being so close suggests it's tidally locked, with one side constantly facing the star and the other side in perpetual darkness. Scientists think the planet has a surface temperature of around 430 degrees Celsius. A report in the journal Science claims Gliese 486b could be our best chance yet of studying a terrestrial planetary atmosphere beyond the solar system. But there's a huge problem with that. You see, red dwarf stars are known for having a lot of stellar activity, things like stellar flares and coronal mass ejections, events which could easily destroy an orbiting planet's atmosphere and irradiate anything on its surface. Still, it is a super-Earth, and that's exciting, because we don't have any super-Earths in our solar system. Like Earth, Gliese 486b is a rocky terrestrial world, but really that's where the similarities end. Firstly, it's 30% bigger and almost 3 times more massive than the Earth, so gravity on this world is something like 70% stronger than on Earth. Super-Earths themselves aren't rare, but Gliese 486b is special for 2 key reasons. Firstly, if it has retained an atmosphere despite being so close to its host star, then the intense heat would cause that atmosphere to expand, helping astronomers undertake atmospheric measurements. And secondly, it's a transiting planet, so it crosses in front of the star as seen from Earth. And as a transiting planet, Gliese 486b will give scientists 2 unique opportunities to study any atmosphere that's there. Firstly, when the planet passes in front of the star and a fraction of starlight shines through the atmospheric layer. That's a technique called transmission spectroscopy. And then again when starlight illuminates the surface of the planet as it orbits around behind the star, a technique known as emission spectroscopy. In both cases, scientists will use a spectrograph. That's a tool that splits light into its component wavelengths, allowing scientists to decode the chemical makeup of an atmosphere. The findings were made using NASA's TESS, Transiting Exoplanet Survey satellite, together with ground-based telescopes in Spain, the United States and Chile. One of the study's authors, Dr. Ben Montet from the University of New South Wales, says Gliese 486b is the kind of planet astronomers have been dreaming about for decades. And studying any atmosphere on this super-Earth will help astronomers better understand how it's affected by its host star.
Gliese 486b is one of the nearest transiting planets we know of. It was discovered using data from the NASA TESS mission, which is a search for transiting planets. So by transiting, I mean it passes between us and the star along the line of sight to the star on its orbit. And so when we observe the star over and over, we see that the planet casts a shadow on the surface of the star. So in this case, the planet has a very short orbital period, about 36 hours. So every 36 hours, we see the star appear to get slightly fainter. This is just the shadow of the planet going in front of the star. The star itself is not changing brightness, just our perception of it. And so when we see this over and over, that can tell us quite a bit about the planet. The period of the shadow event tells us about the year on the planet, how long it takes to go around its star. And the depth of the dips, how deep the shadow, the transit event is, tells us about the size of the planet. And so with that information, we could see that this planet is only a little bit bigger than the Earth, about 30% larger, and then follow up spectroscopic observations. So looking for the Doppler signal as the planet and the star orbit each other and the star moves towards and away from us and is blue shifted and red shifted, tells us about the mass. And so we can see that about 2.5 times the mass of the Earth. So those two pieces together tell us this planet is rocky. We call it a super Earth, just meaning a rocky planet slightly bigger than the Earth. And because it's so close to the star, it's very hot. It has a temperature of something like 430 Celsius, about 700 Kelvin.
It's also relatively close, an interesting opportunity to try and study the planet's atmosphere, assuming it's got an atmosphere, of course, being so close to a red dwarf. And let's face it, red dwarfs are very excitable. There might not be much of an atmosphere there.
Absolutely. And that's one of the very big questions we have. The star is very different than the sun. M dwarfs have very strong magnetic fields, large flares, lots of magnetic activity that could destroy a planet's atmosphere. We know, M dwarfs are potentially a promising place to look for signs of life. Rocky planets are very common around M dwarf. They seem to be the most common type of planet around M dwarf. And M dwarfs are the most common type of star in the galaxy. They're about 70% of all the stars. Putting those two together, most rocky planets are around M dwarfs. So it's an attractive place to look, but there's then the question, can M dwarf planets retain their atmospheres, or are they destroyed by the star's magnetic activity and high energy material falling off of the star? That's the problem. Once you lose your planet's atmosphere, you're not getting it back. There's no real way to recover atmosphere. Once it's gone forever. So we really want to understand what the atmospheres of planets around M dwarfs look like. This is one of the best opportunities we have for that. It's not really, an Earth-like atmosphere. It's so, if it has one, it's so hot, the planet's probably more like Venus than Earth. But this is the best planet we have to potentially measure the atmosphere of a planet around an M dwarf. And so if this planet has an atmosphere, that's a really good sign for future, more temperate planets around M dwarfs that we discover. That will be the potential types of systems that we observe with James Webb and its successors in the search for biosignatures.
What's the difference between a super Earth and a mini Neptune?
A super Earth is a planet that has still a rocky surface and a thin atmosphere. It can have an atmosphere, but not a very thick one. It's one that you could potentially live on, or at least visit. So something like Venus and Earth and Mars in broad strokes. Where a mini Neptune would be something that has a very extended atmosphere, much like our gas and ice giants in our solar system. So something that doesn't really have the surface where light penetrates to that you could imagine living and breathing. And so mini Neptunes are smaller than Neptune, but with that extended atmosphere. Super Earths are the rocky planets that are kind of scaled up versions of the Earth. And we think the border is usually somewhere around 1.5 times the radius of the Earth, 1.5 to 1.7. Where smaller than that, you're more likely to have the rocky surface, and bigger than that, you probably have the big atmosphere.
Does one become the other as the stellar wind from the host star blows atmosphere away?
We don't really know. That possibly happens sometimes, that you could have this very big atmosphere that gets stripped away, and then you're left with the core of what was the core of the giant planet. We think we see some planets that, especially found by Kepler, that are probably, that is the explanation. Very, very close to the star, probably had a larger atmosphere to begin with. We don't think that's always the case. In our solar system, probably the giant planets formed first over the first 10 million years or so of the star's life, of the sun's life. And then the inner planets, the Mercury through Mars, formed a little later out of the remnants of the protoplanetary disk once a lot of the gas and dust had dissipated. And so we don't think that our own planet went through a stage of being like a mini Neptune that then got tidally or photo-evaporated away. But for some planets very close to their stars, we think that's definitely a possibility.
We look at our solar system, we don't see any super Earths or mini Neptunes in it. Are we unusual? I think we're starting to look like we're unusual.
Yeah, we seem unusual. So it's important to remember that most of the planets we know, the planetary systems we know, look very different than our own solar system. The planets discovered by Kepler and Tess, just because of the nature of the way they find planets, they're very preferentially biased towards short-period planets. Most of the planets we talk about in the news have orbital periods less than 50 to 100 days. This planet is a day and a half.
Yeah, these are the easier ones to find, but that's why there's a bias there.
Exactly. That's exactly right. The shortest planet in our solar system, Mercury, has an orbital period of 88 days. And so in the scheme of Kepler and Tess planets, that's quite a long period. So we're really probing a population that we don't have in our solar system in terms of where they are relative to their star. But also you're totally right that these are systems that we don't have examples of in the solar system. The next Earth is the biggest rocky planet. The next largest planet is Neptune. That seems weird. Before Kepler, a lot of our models of planet formation were conditioned on what we thought we knew about the solar system and didn't really predict these planets should be very common. But as we've looked with Kepler and Tess, it seems like the mini-Earth super Neptune might be the most common type of planet in the universe. And so we don't have that. That makes us a little weird, but it's really interesting because it gives us a chance to deeply study a class of planets that we don't have in our solar system. We're learning something very new as we try to understand what these planets are, how they form, how they get to be the way they are. It's much easier for us to understand an Earth-sized planet or a Neptune planet because we have beautiful data right here. We can send a probe to them. We can't send a probe to a super Earth or a mini Neptune. And so there's a lot to learn from the Kepler and Tess data.
When you read things like the Nice model or the Grand TAC about how our solar system formed, it all seems to make a lot of sense. Do we see anything in other stellar systems that would fit that sort of a mold, or are we unique in that regard?
Yeah, so it's hard to say specifically about things like the Grand TAC model because that takes place over such a short time period and such a wide physical distance in our solar system. You're talking about things from moving from 10 AU to a couple AU away from the star. And so we're not as sensitive to that area as we'd like to be in the surveys that we're doing. We tend to be biased towards the short period things. But we do definitely see evidence for significant migration of planetary systems. There are a lot of planets discovered, especially by Kepler and Tess.
These are the hot Jupiters.
The hot Jupiters, but also smaller planets in resonance with each other. So two planets will have periods of 10 and 20 days or 10 and 15 days. So their orbital periods are very close to integers of each other. And so we think that's due to planets migrating inward and catching each other gravitationally and then migrating together inward through drag in the disk as they're being formed. And so those plus the hot Jupiters are evidence for really significant migration over the first tens of millions of years of planetary systems in not an entirely dissimilar way to what's predicted by the Nice model.
Where do you want to take this now? Obviously, you want to study the atmosphere as best you can. There are different ways of doing that.
Yeah. So for Gliese 486b, our best bet in the near future is probably James Webb. It's one of the best targets to measure the atmosphere. So there's two ways, broadly speaking, that we measure planet atmospheres. The first is looking at the planet as it transits directly in front of its star, and then we can see light go through the atmosphere of the planet around the edges of it, and then infer what the composition of the atmosphere is at what we call the terminator. It's where the twilight is on the planet between the day side and the night side. And then also half an orbit later for this planet, right before it hits what we call secondary eclipse, when it goes behind the star, we can probe the day side of the planet. So what does it look like on its surface off of reflected light from the star just before it goes behind the star and gets occulted? And so this is the single best rocky planet we know of to do that second type of measurement called emission spectroscopy. And so to understand the day side of this planet, this is the best chance we have with James Webb for a rocky planet. And so I expect that this will be a very high priority target for that telescope once it gets launched.
James Webb's launching in October, November at this stage?
Yeah, current plan is late 2021. It will take a few months to get into its orbit. It's going to go to L2, the Earth-Sun Lagrange point behind the Earth, and then has to unfold its mirror. It'll be calibration checks and commissioning. So I would expect science would start in maybe April 2022.
That's Dr. Ben Montet from the University of New South Wales. And this is Space Time. Still to come, a final mission for the Cygnus 15 cargo ship, and later in the science report, a new study shows we'll need to vaccinate at least 85% of the population in order to achieve herd immunity for COVID-19. All that and more still to come on SpaceTime. A Cygnus cargo ship is undocked from the International Space Station to launch a series of 5 satellites before ending its mission. The Cygnus NG-15 is carrying more than 4 tons of trash destined to burn up during atmospheric re-entry. However, prior to meeting its ultimate demise in the skies above the southeastern Pacific Ocean, the Cygnus will launch 5 small satellites using the Slingshot NanoRacks CubeSat deployers. The Cygnus NG-15 was launched back on February the 20th aboard a Northrop Grumman Antares rocket from NASA's Wallops Island Flight Facility on the Virginian mid-Atlantic coast. It was carrying nearly 4 tons of scientific research equipment and supplies to the space station. The Cygnus docked with the orbiting outpost 2 days later. Once all the supplies were unloaded, it was used to store trash and disused equipment no longer needed by the crew. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. Or forget what the politicians have been telling you, a new study shows we'll need to vaccinate at least 85% of the population in order to achieve herd immunity against COVID-19. The new modelling from James Cook University has implications for the Australian government's 4-step plan to transition from suppression of COVID-19 to a strategy of reopening and returning to normal life. Scientists say the first hurdle, which is to vaccinate and achieve herd immunity, will be more difficult to achieve with the Delta variant of COVID-19 as it's both more infectious and less amenable to vaccination. Researchers found the Delta variant's reproduction number, that is, the average number of people infected by one person carrying the virus, is 4 for the Delta variant. That means 85% of the population will need to be vaccinated using the current strategy. If vaccine coverage was targeted at the most infectious ages, Australia could achieve herd immunity by vaccinating 75% of the population. However, that may not be realistic because it would require nearly 100% vaccination uptake in the 20 to 60-year-old age group. The World Health Organization estimates over 8 million people have been killed by the COVID-19 coronavirus, with over 4.1 million confirmed fatalities and more than 186 million people infected since the deadly disease first spread out of Wuhan, China. A new study warns that night owls, especially those who average less than 5 hours sleep, have an increasing risk of obesity. Scientists characterize the bedtime of midnight or later as late night, and suggest that staying awake at night may suppress the secretion of melatonin, which is associated with an increased risk of obesity, cardiovascular diseases, and cancers. The study, reported in the Journal of the American Medical Association, also was bad news for nappers, which found that longer daytime siestas were also associated with a higher risk of obesity. But the authors suggest that could be because a daytime nap might occur more often due to late nights. Scientists from the Victorian Royal Botanic Gardens have discovered what is now the largest population of Australia's oddest and most critically endangered species of fungus. More than 100 fruiting bodies of the fungus known as tea tree fingers, so called because of their distinctive finger-like form that seemingly grips its wooden substrate like a hand, have been discovered on Victoria's French Island, several kilometres from the Mornington Peninsula. Despite intensive surveys, these exceptionally rare fungus have only ever been found at 4 locations on the mainland since they were first chanced upon by modern scientists back in the early 1990s. Fungi have been historically overlooked by many conservationists. That's despite their crucial role in ecosystems, especially when it comes to decomposition and nutrient recycling. China is continuing its preparations for war, building over 100 new nuclear intercontinental ballistic missile silos. Commercial satellite images have uncovered 119 silos being built in the desert near the northwestern city of Yumen in Gansu province. The new missile silos appear to be similar in design to many of Beijing's existing nuclear missile facilities. During a speech celebrating the Chinese Communist Party's 100th anniversary, Chinese President Xi Jinping boasted that a Great Wall of Steel was being built by the People's Liberation Army. Well, it now seems that one of Canada's best documented UFO stories may have been nothing more than a case of having a little bit too much to drink. Back on May the 19th, 1967, a man received serious burns after he claimed he had gotten too close to one of two glowing objects that had descended from the sky near Falcon Lake in Manitoba. One of these glowing objects landed close enough for the man to approach. But as it took off again, its exhaust set the man's clothes ablaze, leaving him with serious burns. Ufologists claim that hospital images show grid-like burn marks on the man's chest, and a similar grid pattern appears to be burned into his t-shirt. 2 books have now been written on the Falcon Lake encounter, and in April 2018 the Royal Canadian Mint released a $20 silver coin depicting the alleged event as part of its Canada's Unexplained Phenomena series. However, Tim Mendham from Australian Skeptics says a careful review of all the available evidence, including the medical and police reports, concludes that while the man did indeed suffer burns, they appear to have been caused by a hot waffle iron, possibly after he fell over after consuming a large amount of alcohol. It seems the man who was prospecting for silver ore near the lake at the time may have invented the UFO story to keep other prospectors out of the area.
Canada's weird, actually. I mean, most alien abductions you think are actually from the US, which they are, where people tend to get taken away from people in the middle of the countryside where no one else has seen them, etc. They get taken away and brought back later on after being probed, etc. There was
Somewhere
one case...
in the Appalachians, yeah.
Yeah. Well, there was one. Yeah, the one case the famous case in Canada, which was by a fellow who was called Stefan Michalak, which was how he was taken away, and he had scorch marks on his chest and his stomach, which looked a bit like a waffle iron, that sort of pattern. And he claimed that he'd been taken away and probed in that alien craft and brought back, etc. There were reports by the Mounties and all sorts of things. But there's a Canadian researcher who has researched a lot of UFO things. It's very worthwhile having a look at his site, which is called theironskeptics.com. He's from a skeptical point of view rather than from a pro-UFO belief background, and he's done quite a good report on it. It's actually a good example of not private investigator, that makes it sound like a detective, an amateur investigator going after particular cases and things, and spending quite considerable time and research looking into some of these things, as much as you can when you weren't there, to see what sort of stories you're relying on. It's often just the person themselves, the probee, and perhaps some other people that they might have reported the case to. But this Stefan is an interesting story of an abduction in Canada, and even more interesting is this debunking. So
Tell us a
little
bit about the debunkingness of it. How was it? What did it turn out to be? Did he fall on a waffle iron or something, or what?
Mainly inconsistencies in his story about what happened to him, how aware he was, all sorts of different things that just don't make sense, that he changed his story, as people do many times,
It's always the little things, that the big story.
The thing about the burns on his...
The little things.
Yeah, the little things that you get caught up on. The burns on his stomach, the suggestion is there's nothing extraterrestrial. All they prove is that he was burned. The question is, this fellow said, give me a potato masher and a campfire and he can duplicate it. It's a large potato masher, I should add, actually. So whether it's a waffle iron or a potato masher.
Everybody knows that if you're abducted by aliens, you're probed anally. That's what it's all about.
They don't mention the potato masher. Painful. He suggested that the fellow might have been having a few drinks and might have fallen on a potato masher, a hot potato masher or something. I don't know.
That's the excuse nurses hear in medical wards all the time.
Yeah, I was drunk and I fell over. Yes. And the suggestion is that he probably could have done it to himself, believe it or not. Shock horror.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air access to our exclusive Facebook group and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.